Hi, this is an example problem enumerating quantum states from chapter 30. We're going to learn how to write out and describe, count in other words, the various quantum states. It's a little tricky at first, but we're going to figure out how this goes. So for this problem, it says for the n equals 2 shell of the quantum mechanical model of hydrogen, do the following. Part A says list all possible subshells L and label the subshells with the symbols used in chemistry. So N, as you see here, this is a quantum number, so is L, so is M sub L. And there's a hierarchy to these quantum numbers. I'm going to go ahead and show some notes here. We call N the principal quantum number. It can have any integer value, 1, 2, 3, 4, etc. L is the orbital quantum number, and the values of L that you can have, they depend on what N is. So there's a hierarchy here. First, you figure out what N is, then you know what possible values of L you can have. M sub L, the magnetic quantum number, the values of M sub L you can have for each value of L, it depends on the value of L here. And finally, we have M sub S, a final quantum number, which is two different spin states of the electron. So for the n equals 2 shell, and when we say shell, we mean all of the quantum states that have n equals 2. We want to figure out in part A, what are the possible subshells? Subshells are all the quantum states with a given L value. So n equals 2. I'm going to put it right down here below here. What values of L can we have here? Well, let's go look and see what it tells us. The allowed values are, I can go from 0 up in integer values, 0, 1, 2, up to 2 minus 1. For us, we're looking at this. We're looking at n equals 2, 2 minus 1. We can only go up to 1, so we either get to have 0 or 1 in this case. So we've got L equals 1. Oh, I guess I'll put 0 first. 0 or L equals 1. And they also ask us to label these subshells using the chemistry terminology. Let's go ahead and look at that real quick. So for the shells, we really just use the N value here. For the subshells, we often use, instead of, or along with the L values, we'll use these SPD, which you may be familiar with from chemistry. So for 0, we've got S. For L equals 1, we've got P. So this guy here, this is a S, and this is a P subshell. All right, now let's see what it says for part B. Keep on going here. Part B. List all the orbitals in each subshell. So M sub L is the quantum number that distinguishes a specific electron orbital or electron cloud shape. And for each L, there's a certain number of orbitals you can have, and that depends on this equation here. Whatever the value of L is, you can have different orbitals that range from minus L up to plus L. Now, if L equals 0, then it's only going to be 0 because you go from 0 to 0, that's it, right? So in this case, we're going to have for L equals 0, there's only one possible orbital. It's going to be M sub L equals 0. And now we can go look for the other possibility where we have L equals 1. Going back to the equation, well, if L is equal to 1 now, I can go from minus L to plus L in that integer increment. So we're going to go from minus 1 to 0 to plus 1. So we write that down. We're going to get M sub L equals minus 1, 0, and plus 1. And so that's what we were asked for in part B. We've got 4 different orbitals in the n equals 2 shell. Three of them are p subshells. these guys, and one of them is an S subshell. Part C asks, determine the total number of distinct electron orbitals and states in the n equals 2 shell. Okay, so if we look at this, each one of these guys is a distinct orbital. So we've got 4 orbitals in the n equals 2 shell. And for each of the orbitals, you can always house 2 electrons. So the spin quantum number m sub s, minus 1/2 plus 1/2, that relates to the electron spin up or down. You can have 2 possible states of the electron spin per orbital. So that duplicates the orbitals, the number of orbitals, by 2 to get the total number of electron states. So this guy times 2, spin up or spin down for each orbital, that's going to give us 8 distinct quantum states. Now I want to show you how we can organize these nicely. So in the book it shows you a picture. You can see it right here of how we organize these. I'm going to go ahead and just paste that into the problem here real quick. And you can see that this is organized similar to the way that I organized it above. They happen to put the L equals 1, the P subshell right here, and below there they put the L equals 0, the S subshell. But here's your shell, n equals 2. Here are the subshells. You can go 0 or you can go 1 for L, the S and P orbitals. S and P subshells. And for the orbitals, again, we've got just a single orbital for the S, and you got 3 p orbitals. Again, given by the m sub L value. Finally, you can duplicate each of those orbitals with an up or down, plus 1/2, minus 1/2 electron spin. You can see it there. And we can actually write down each set of quantum numbers for every one of these distinct electron states. So for example, like let's look at the first state here, right? That's going to be n equals 2, L equals 1, m sub L equals plus 1, and m sub S equals 1/2, right? As you look at the other 7 states, they're all distinct. They each have a distinct set of quantum numbers there. So that is how we enumerate quantum states. Practice it a few times until you get the hang of how this works.